Okay, so welcome back to another video. So here we are given two different representations of gamma, and so we have one that's derived by Gauss and another one derived by Weierstrass. So Gauss's definitions of gamma says that we have the limit as n approaches infinity of n to the power s divided by s multiplied by the partial product of k divided by s plus k. And as for Weierstrass's definition, we have e to the power negative lowercase gamma, otherwise known as the Euler-Mascheroni constant, multiplied by s divided by s, and then multiply with the infinite product series of e to the power k divided by s, multiplied with the inverse of 1 plus s over k. And of course, with the gamma function, this is valid for all complex number s, except for the non-positive integers. So we'll be actually deriving by proof two of both of Gauss's and Weierstrass's definitions of the gamma function. And what's nice is that I chose for two because, for one, when we're working on the proof for Gauss's definition, it follows that for Weierstrass's definition, we actually use this Gauss's representation of the gamma function to help complete the proof, and then represent the rest of this, of course, with the product series and some algebra and all that manipulation. What's even a bit of a twist is, of course, we have the Euler-Mascheroni constant. So as we derive for his proof, we're going to have to take things a little bit of careful consideration with the definition of course, the Euler-Mascheroni constant. So from all this, for Gauss's representation, we start off, we consider with an integral. But before we get into that meat of the integral, rather the proof of Gauss's representation, there's some things that we want to pay attention to for that said considered integral we're going to look after. So with that, let's actually just jump right in and get the proof started. So we're going to consider the integral s sub n, and that says that we have the integral from 0 to n of t to the power s minus 1, then multiply with 1 subtract t divided by n to the power n, and then dt. So let's say that if we actually take the limit as n approaches infinity, so on the left-hand side we had the limit as n approaches infinity of s sub n, then we say that, of course, taking the limit over here as well, n approaches infinity of our said integral. Then, interestingly, what I can do from here is I can actually bring the limit inside, and of course that just approaches infinity, so I'll change that to the proper integral for our bounds. So infinity, then t to the power s minus 1, then with the limit as n approaches infinity of 1 minus t divided by n to the power n, then dt. Take a look at this. You'll notice that this is actually in a form of a well-known constant. And what does that turn out to be? This is actually going to approach e to the power negative t. If this was positive for this sign, then that means that would be e to the power t. But since this is negative with that association, so this is going to be e to the negative t over here. And then we're going to put that substitution in. So this is going to be the integral from 0 to infinity of that same thing, t to the s minus 1, then multiply with e to the negative t dt. But what is this? This is exactly in the same form of the gamma function itself. So that means this is actually equal to gamma of s. And so that's nice to say that this integral is, as we take this as n approaches infinity, this is going to indeed converge to the gamma function. Instead, let's actually find a little closed form representation of just our s sub n and not worry about the n approaches infinity into that stance. So at least we have an idea of if there exists a closed form representation for this in order to get to what we need to for Gauss's representation of gamma. So this is where the actual proof starts. So with this definition, of course, that's what we did for applying, the n approaches infinity for that convergence, for that limit. So what we can do here is, how do we evaluate this integral specifically? Well, let's actually do some integration by parts and see where that takes us. Suppose that if we let u be the one to perform the derivative, so that means we're going to let u equals 1 minus t divided by n to the power n. Then we have that du is going to equal to negative n divided by n multiplied by 1 minus t divided by n and then to the power n minus 1, then dt. Okay, and so if we choose the one, our function that we want to integrate, so dv is equal to t to the power s subtract 1 dt, then of course v is going to equal to t to the power s divided by s. And of course, we have that n divided by n, that's going to equal 1, but I'm actually going to keep it into this notation just so you'll see that where I'm coming from with this, that it actually gives some sort of pattern that we're actually going to investigate later on. So s of n so far, so we have our s of n right here for this integral representation that we consider. So putting all this back in for after applying the integration by parts, So we have 1 minus t divided by n, and then to the power n, multiplied by t to the s divided by s, and we evaluate our bounds from 0 to n. Then we subtract, but of course I can actually factor out the minus here, so this will become a plus. And then I can factor out the n and n over here, and then factor out the s, as this does not depend on our integral in terms of t. So this is plus n divided by n times s, then multiply with our integral from 0 to n of t to the s, then multiply with 1 minus t divided by n, then to the power n minus 1 dt. And so if we actually plug in our bounds here, so if I plug n, then that means this is going to be 1 minus 1 is 0, and then the whole thing just, goes to 0. 0 is the same thing, so that's fine. So this thing completely disappears, and then we're just left with this integral over here. So this is what I'm going to have to put as we have so far. Let's actually yet again do another integration by parts. We're actually going to use the same format just like before. We'll let this now in this situation, now the exponents decrease by 1, and then we're going to integrate this, except this is actually increased by 1. So we're going to let u equals 1 minus t divided by n to the power n minus 1, then du is going to equal to, so taking that derivative, so we have negative n minus 1 and then divided by n, multiplied with 1 minus t to the t divided by n, and then n minus 2 dt. We choose our dv. Of course, we can say that this is t to the s, then dt. Then v is going to equal to t to the s plus 1, and then divided by s plus 1. Okay, and so from here, let's actually plug this all back in. So now, so far, our s sub n again is going to be n divided by s. Then that means if we put in the parentheses from this integration by parts we apply to, so we have t to the s plus 1 divided by s plus 1, multiplied with 1 subtract t divided by n, and then to the power n minus 1, then we evaluate this from our bounds from 0 to n. Then add this, let me move on to the next line for this, plus this could be n minus 1, then divided by n times s plus 1, multiply with the integral from 0 to n of t to the power s plus 1, then multiply with 1 minus t divided by n, then to the power n minus 2, then dt, and then I'm going to close this parentheses off. So again, same thing, we can just apply, well, not really apply, but substitute, evaluate the values for n, but again, this is actually going to approach 0 for this value over here. So far now, our s sub n is going to be n times s, or n divided by n times s, then multiply with n subtract 1 divided by n times s plus 1, then multiply with the integral from 0 to n of 1 minus t divided by n to the n minus 2, then multiply with t to the s plus 1, and then dt. So let's actually apply this one more time, and then we can actually evaluate. Let's actually make some observations from here. So if we do this again one more time, so this is applying integration by parts the third time. So suppose that if we do use the same pieces and formats just like that. So we let u equals 1 minus t divided by n, and then n minus 2, then du is going to equal to n minus 2 and then divided by n, well, negative, and then n minus 2 divided by n, then 1 multiply with 1 subtract t divided by n, and then n minus 3 dt. Then we have dv, if we choose that, that's going to be the t to the power s plus 1, then dt. Then v is going to equal to, integrating this is going to be t to the s plus 2, and then divided by s plus 2. Okay, and so let's actually plug that back into our s sub n yet again and see what we can see, what we have from here. So s sub n is going to be this following right here. So far we have n divided by n times s, then times n minus 1. Let me actually just jump to the next clip and then to finish writing all this out. So everything this is written that we combine integration by parts, and then as you see again that if I just plug n back into over here, this is going to approach 0, and so now everything of course is going to be written as follows. So n divided by n times s, then n minus 1 divided by n times s plus 1, multiply with n minus 2 and then divided by n times s plus 2, and then we have our integral from 0 to n of t to the s plus 2, and then multiply with 1 subtract t divided by n, and then n minus 3, then dt. So let's stop here for a bit and let's actually make some observations. So what can we notice here? So every time we actually do each integration by parts iteration, we notice that specifically the exponent of our 1 minus t over t divided by n quantity, it actually decreases by 1. So for example, if we applied the first integration by parts, that decreased to n minus 1. We do it a second time, that decreased to n minus 2. We do it a third time, then that means that's n minus 3. So what that means is that if we were to do the iteration all the way up to n iterations, so that's a n minus n, aka that's going to be 0. So that's nice to say that that's actually going to cancel out the, well really that's going to mean that's going to approach to 1, since any quantity to an exponent 0 is going to equal 1. And then what about the t, starting off with our t to the power s minus 1, if we apply the integration by parts yet again, we see that for each iteration that also, but instead not decrease, but increases by 1. So again, applying the first IBP, that goes to t to the s. The second time, so t to the s plus 1. Keep going on so forth after n iteration. Instead, that's actually going to give us t to the s plus n subtract 1. And so we can actually can prove all this by induction, but assuming that the pattern continues, so let me actually erase this side of the board and continue the work from here. So with the pattern continuing, we're going to have that we have s of n is going to equal to n divided by n times s, then n times, or rather n minus 1 divided by n times s plus 1 times n minus 2 divided by n times s plus 2, then keep going so on so forth. Then this is actually after n iterations, just like we discussed, we're going to give us that this is 1 divided by n times s plus n minus 1, then multiply with the integral from 0 to n of t to the power s plus n subtract 1 dt. And this is nice that this is actually a very easy iterated integral to calculate. And by performing this calculation, we have 0 to n of t to the s plus n minus 1. I just reset, just saying things repeatedly. We can see that by power rule, so t to the s plus n, and then that's going to be s plus n. Evaluate this from 0 to n, and of course, that's going to give us n to the power s plus n divided by s plus n. In other words, that we can actually write this as the same thing as n to the power s multiplied with n to the power n, and then divided by s plus n. Okay, and so we substitute this back all in. So that means, so s of n, again, I have to rewrite this again. So let me actually rewrite the first couple, lines rather, and then get to where we need to give the explanation. So after all this expansion over here, so s of n, then the last part is just multiplying the n, just substituting the n to the power s, then n to the power n, and then s plus n. So what you'll see is that everything on the denominator has common factors of n, so this is actually another way of saying this is n to the power n however many times, meaning that this is actually going to cancel both the numerator and denominator, sharing the n to the power n. And so now that actually notices that we have an s plus n to the bottom over here, and then, well, that leaves us with just everything with s plus n, and then each iteration for just s. And then now what that gives us is that if we actually simplify all this out together, we're actually going to get in a nice product form and say that this is n to the power s divided by s multiplied with the product series, so the partial product series from k is equal to 1 to n of k divided by s plus k. Okay, and so therefore the left-hand side over here is going to equal the right-hand side over here. So what's nice is that if I now finally take the limit as n approaches infinity, so the limit as n approaches infinity of s sub n, we said that earlier just from that whole derivation that we considered that function earlier, that it actually approaches gamma of s. But in other words, that means taking the limit of this side as well is indeed going to give us the derivation that we want to show for Gauss's representation of gamma. So indeed, this is the limit as n approaches infinity of n to the power s divided by s multiplied with the product series of n, and then k is equal to 1, and then k divided by s plus k, which indeed just completes the proof for Gauss's representation of the gamma function itself. So with that, that's all great. So let's actually move on to now, moving on to Weierstrass's definition of gamma. Okay, so now moving on, we have Weierstrass's theorem to derive. So a little bit of some interesting things is that Weierstrass's definition for gamma is actually used heavily in context for the digamma function, but his definition also can be used to help prove Euler's reflection formula, which I thought that's actually a really neat technique to actually help prove it with that definition, which I did not know about. That's cool. So with that, let's actually start with proving his definition, and we're going to start off by actually using Gauss's representation, which is a follow-up to what we just proven to help establish everything that we want to derive for, again, Weierstrass's definition. So we start with Gauss's representation of gamma s, which I would say recall, but literally the clip is just literally a couple seconds later, so you're already seeing what you need to see, but I'm going to write this again. That Gauss's definition of gamma is written as the limit as n approaches infinity of n to the power s divided by s, and then multiply with, you already see it's on the top right there. And so from here, what we can do is, as a bit of a clever technique for n to the power s, we'll write this in forms as an exponential. So specifically, I'll write that as n to the power s is the same thing as e to the power s, and then multiplied by ln of n. And there has to be something we have to deal with in order to achieve the Euler-Mascheroni constant in part of this process of the derivation. So let's recall that the Euler-Mascheroni constant, lowercase gamma, is written in the form of the following limit. That is to say that n approaches infinity of h sub n, which is the nth harmonic number, and then subtract this from ln of n. Okay, and so what we can do from here is we can actually, with this, let's actually rewrite our e to the power s ln of n as a bit of a clever trick that we can actually, do a little bit of fixing up. So this is the same thing as to say that this is actually in the form of a cancellation. So this is going to be, say, as, of course, e to the power s and then ln of n. We're going to add and subtract, so s to the power, or s times h sub n, and then add this with s times h sub n. We get the the Euler-Mascheroni constant in our exponent, and now we actually substitute back for the Gauss's definition of gamma. So gamma of s so far is what we have is the limit as n approaches infinity, then everything on the above is e to the power s, then ln of n, subtract sh sub n, add this with sh sub n, all this being divided by s, and then of course just the product series of k equals 1 to n of s, or k divided by s plus k. And so let's actually note something that we want to consider. So note, we see that the limit, we're actually going to pay attention in forms of the commutativity. So specifically, we're looking at s times ln of n, and then subtract h sub n. So if we pay attention to that as we take the limit for the continuity's sake of that, so as n approaches infinity, s ln of n, then subtract sh sub n. In other words, I can actually factor out the negative s. So let me put this right here. So negative s multiplied with the limit as n approaches infinity. Then I'm going to actually just switch the terms since there's the negative s involved. So that means we have h sub n, then minus ln of n. And then so that's actually going to equal, of course, by definition from the Euler-Mascheroni constant over here, lowercase gamma. So just substitute that back in. So that's negative lowercase gamma and then multiplied by s, which is nice since that's actually part of Weierstrass's definition right here. So make that substitution. So now gamma of s, so far what we have now is that this is going to be the limit as n approaches infinity of e, and then negative gamma s plus s times h sub n divided by s. Then we have our product series yet again. Nothing has changed from that just yet. Then what I can do is, of course, I can actually factor out the e to the negative gamma s divided by s as well, since that does not depend on our, with the limit as n approaches, or for our variable specifically. So this is e negative gamma s divided by s, then the limit as n approaches infinity of e, then sh sub n, then multiply with the partial product, k is equal 1 of k divided by s plus k. So what we can do here, let's actually divide k to both the numerator and denominator of our product series. So applying that, so far this is the same thing just as written as before. So after applying the division with k, so we have 1 then divided by 1 plus s divided by k. Here's something we have to pay attention to now. So we have e to the s times the nth harmonic number. So how do we actually do something like this that we want to at least get rid and isolate the h sub n notation? So let's actually notice that s times h sub n. In other words, we know that by definition h sub n is is a harmonic number, so it's actually in the partial sum of the harmonic series. In other words, this is the partial product of 1 divided by k, then you just multiply the s, since that's just a constant, not associated with that. So it's n, k is equal 1 of s divided by k. Now what we could do is let's actually take the exponential of both sides. So we have that e to the s h sub n. So by continuity, so this is e, and then with the partial sum yet again, k is equal 1 of s divided by k. So if I were to expand this out, this was the right hand side, so this is e, and then we have s, add this with s over 2 plus s over 3, plus so on and so forth, then all the way up to the nth term, so s divided by n. So we know that with the sum of the exponents, we can actually write this in terms of products. So this is e to the s times e to the s divided by 2, so on and so forth, all the way up to e to the s divided by n. Of course, this is actually nice to say that this is actually in a form of a product series. So specifically, we have that this is just the nth product series of e to the s divided by k. So that's actually nice since we have that we want to verify for this deprivation over here, so that's great. So if we just plug all this back in, so now gamma of s, of course, is going to still equal e, then negative gamma s divided by s, with the limit as n approaches infinity of the partial product series n k equals 1 of e to the s divided by k. Then over here, this is times 1 divided by 1 plus s over k. But in other words, we can write this as the form of an inverse. So again, put this back in, and then also jump one more step in. We're just gonna take the limit as n approaches infinity, but that basically just said we're just gonna replace the n for infinity of that product series. So infinity, k is equal 1, then e to the s divided by k, and then put in 1 plus s divided by k, and then inverse, so the negative 1 power. And so just like that, that actually completes our deprivation proof for Weierstrass's definition of the gamma function, and that also completes the video as we actually completed both deprivations of Gauss's and Weierstrass's definition of the gamma function itself. So there we have it. So yeah, that's pretty cool if you ask me.